In the past lessons, we talked about control, how to choose the commands so that we can achieve a specific objective. For example, having a ducky bot stay in the lane. Control methods cannot be used by themselves to generate reasonable motion in an environment with obstacles. For that, we need to use planning. Planning is what provides the reference signals which the control methods assume to have. Planning takes into account more information about the environment around the robot and what are the long-term objectives. Let's look at the differences between planning and control. You can think of control as being concerned with the here and now, while planning is concerned with the longer horizon. If we want to quantify this difference, we could say that a control process typically works at 10 to 100 Hz. The frequency depends on the inertia of the vehicle. Think of a truck versus a sports car. Planning instead works at lower frequencies. Planning computes every once in a while a trajectory, or more generally a plan, which the control process will try to execute. Control has a short horizon. There are control methods that rely on predicting the evolution of the world, however, that is typically within a horizon of, say, up to 2 seconds. Instead, planning methods take into account the evolution of the world over a longer period of time. The trade-off is that control has a simplified view of the problem. For example, control methods might ignore the obstacles in the environment or just follow simple bounds passed by planning. Instead, planning needs to navigate in a complex environment. Control works on a limited time horizon, so sometimes it's enough to consider a simplified platform dynamics, such as linearized dynamics. Instead, planning must provide plans that are feasible when considering the full nonlinear dynamics of the system. The objective of control are local. A controller is concerned with tracking a trajectory, perhaps with other local objectives, such as maximizing the comfort. Instead, planning needs to make sure that the mission is fulfilled. Solution methods for planning and control have a distinctive flavor, even though there can be some overlap. Control methods for AVs are not AV-specific. They are general-purpose methods. Instead, for planning, we need to use methods that are ad hoc for the vehicle platform dynamics and for the geometry of the environment. For AVs, there are different types of planning problems. An AV needs to plan around the obstacles in front of it, and it also needs to be able to navigate across town. A common approach is to decompose the planning problem hierarchically so that we can be more efficient by exploiting the structure of the problem at each level of abstraction. At the top level, we might have a centralized fleet planning system that gives commands to the single car. For example, where to pick up the next passenger or where to go to wait for new passengers. Suppose the car is given an address at which to go. The next step would be to plan the route to take by looking at the road network and taking into account the predicted traffic on each road segment. At a lower level, the system could think in terms of tactical maneuvers, for example merging, parking, passing, or waiting for a green light. Lower, we reach the point where the system thinks in terms of planning trajectories in state space. Once we have a nominal plan for a trajectory, we still need a layer that is able to respond quickly to changes in the environment. This can be a local obstacle avoidance method that updates the nominal plan at a much faster rate. We have a trade-off warning to recognize. More level of abstractions make the problem intuitively simpler for a human to conceptualize. However, the system is less robust because there are more assumptions that can be violated, and less performant because by introducing layers, we restrict the set of possible behaviors for the system. There exist no tractable, scalable, general planning methods that take into account everything we need for a self-driving car. Rather, there is a large variety of planning methods, each one with its trade-offs. Let's describe some of the trade-offs dimensions. First, we must ask, at which level of abstraction does the method work? Is it at the level of route planning or trajectory planning? What are the assumptions on the optimization objective? Is it a scalar cost function? Is it a logic formula to be satisfied, or what else? What is the output of the method? Does it give us an open-loop nominal plan or a feedback policy? How is the output represented? We can then ask about the assumptions about the scenarios. Does the method work with the robots? Does it have some assumption about the robot morphology or the dynamics? What are the assumptions on the environment? Does the method work in static environments only? Can it deal with moving obstacles? How is the environment represented? Does the method expect a polygonal map, an occupancy grid, or what else? What are the assumptions on the other agents? Can they see the AV? Do they have an adversarial or collaborative behavior? Is there a notion of uncertainty? How is uncertainty represented? Can we model noise in the process evolution, also called aleatory uncertainty, as well as uncertainty in the model itself, also called epistemic uncertainty? Does the method work on the state space, or does it work in information space, and therefore can account for limited information? What are the guarantees, if any? We will later introduce the concepts of completeness, which means that the method finds a solution if one exists, as well as notions of optimality and their probabilistic counterparts. What are the computational requirements of the method? How do these scale with the complexity of the state space and environment? Can resource consumption be amortized if similar queries are repeated? Can the algorithm be parallelized? In the following classes, we will see various planning methods, and we will see how they rank against each other along these dimensions. Let's summarize what we've seen today. Planning is what AVs use to generate behavior over a longer time horizon. It is complementary to control. A key approach is to use hierarchical decomposition of the planning problem. There exists no generally applicable planning method. Rather, there is a large variety of different methods that can be evaluated along different dimensions. In the next lessons, we will see some of these methods.